Ever wondered why you see the world the way you do? How is it that we can describe shapes, patterns, and structures in a way that everyone understands? Much of this comes down to analytical geometry. This brilliant branch of mathematics, also known as coordinate geometry, elegantly combines geometry and algebra to make sense of our world. It's like a secret language, allowing us to represent complex geometric shapes through simple algebraic equations. But analytical geometry isn't just about shapes and equations. It plays a pivotal role in fields as diverse as physics, engineering, and computer graphics. It's the hidden force that allows skyscrapers to stand tall, bridges to span wide rivers, and video games to create immersive virtual realities. Every time you marvel at a breathtaking piece of architecture or lose yourself in a video game, you're experiencing the magic of analytical geometry. So, next time you marvel at a stunning piece of architecture or enjoy a video game, remember the unsung hero, analytical geometry. The story of analytical geometry is a tale of two brilliant minds, René Descartes and Pierre de Fermat, two giants of the 17th century who independently yet concurrently paved the way for a new branch of mathematics that would revolutionize our understanding of the physical world. René Descartes, a French philosopher and mathematician, is often considered the father of modern philosophy. But his contributions to mathematics are equally profound. Descartes' genius lay in his ability to see connections where others couldn't. He recognized a fundamental link between geometry and algebra, two fields that were considered separate until then. He introduced what is now known as the Cartesian coordinate system, enabling geometric shapes to be represented as algebraic equations. This was groundbreaking, as it allowed complex geometric problems to be solved algebraically, simplifying the process significantly. On the other hand, we have Pierre de Fermat, another French mathematician. Fermat may be best known for his last theorem, but his work in developing analytical geometry was equally significant. Fermat's approach was slightly different from Descartes'. While Descartes used algebra to solve geometric problems, Fermat used geometry to solve algebraic ones. He developed methods for finding the maxima, minima, and tangents of curves, which are foundational principles in the field of calculus. Despite working separately, their contributions were complementary. Descartes' Cartesian coordinate system provided a practical method for representing geometric shapes algebraically, while Fermat's techniques laid the groundwork for the calculus needed to study these shapes in depth. Together, they created a new mathematical landscape, where geometry and algebra were no longer separate entities, but two sides of the same coin. This fusion of algebra and geometry was the birth of analytical geometry. It opened up new avenues in mathematics, physics, engineering, and other disciplines that rely on a precise understanding of the physical world. Despite working separately, both Descartes and Fermat played crucial roles in what we now know as analytical geometry. From its humble beginnings in the 17th century, analytical geometry has grown and evolved to become a cornerstone of modern mathematics. Let's take a stroll down the memory lane of analytical geometry. After the initial development by René Descartes and Pierre de Fermat, the field saw a significant evolution in the 18th century. The introduction of calculus by Sir Isaac Newton and Gottfried Wilhelm Leibniz added a new dimension to analytical geometry, allowing the study of curves, surfaces, and solids in a more profound manner. Fast forward to the 19th century, and we see another notable advancement with the advent of non-Euclidean geometry. Mathematicians like Carl Friedrich Gauss and Nikolai Ivanovich Lobachevsky challenged the conventional wisdom of Euclidean geometry and introduced concepts of curved spaces, laying the groundwork for Albert Einstein's theory of relativity. The 20th century marked a major milestone in the evolution of analytical geometry. Mathematicians started exploring higher dimensional spaces and complex numbers, leading to the creation of complex geometry. This has been instrumental in understanding the nature of quantum mechanics and string theory. In recent years, the field has been further enriched by the advent of computer technology. Computers have made it possible to visualize and analyze complex geometric shapes and patterns that were previously unimaginable. Moreover, the use of computers has greatly enhanced the application of analytical geometry in various fields, like physics, engineering, and computer graphics. Throughout this journey, countless mathematicians and scientists have contributed to shaping analytical geometry. Each new discovery, each new idea has been a stepping stone, leading us to our current understanding of this fascinating field. As we can see, analytical geometry has come a long way since its inception, and it continues to shape our understanding of the world. The secret sauce of analytical geometry? It's all in the coordinates. Now, when we talk about coordinates, we're referring to a set of values that provide a precise location within a given space. Think of it like a treasure map. X marks the spot. But instead of just one X in analytical geometry, we have a whole grid of X's and Y's, each representing a unique point in space. This grid of coordinates, known as a coordinate system, is the backbone of analytical geometry. It's like the stage where our geometric actors, lines, curves, figures, come to life. And this isn't just a two-dimensional stage. Oh no, with coordinates, we can create a three-dimensional world and beyond. But how do we describe these geometric actors using coordinates? Well, we use equations and inequalities. A line, for instance, can be described by a simple linear equation that relates the x and y coordinates. A curve might need a more complex equation, perhaps involving squares or cubes of the coordinates. And a figure. That could be represented by a system of inequalities, defining the boundaries of the shape. The beauty of using coordinates is that it gives us a common language to describe these geometric shapes. It's like having a universal translator for geometry, and this isn't just theoretical. Coordinates are used every day in fields like physics, engineering, and computer graphics. Think about it. How would an engineer design a bridge, or a physicist calculate the trajectory of a satellite, or a game designer create a virtual world without using coordinates? It would be like trying to paint a masterpiece without a brush. So, when we talk about the power of coordinates, we're really talking about the power to describe and understand the world around us. From the smallest molecule to the largest galaxy, everything can be represented using coordinates. With coordinates, analytical geometry gives us the language we need to describe the world around us. So, we've taken a journey through time, from the birth of analytical geometry to its modern applications. We kicked off our adventure with the role of analytical geometry, exploring how this fascinating branch of mathematics intertwines geometry and algebra. It's a tool that simplifies geometric shapes, transforming them into algebraic equations, and vice versa. A seemingly complex sphere can be reduced to a simple equation, and an intricate equation can bloom into a beautiful geometric shape. We then traveled back to the 17th century to the birth of analytical geometry. We met its parents, René Descartes and Pierre de Fermat, who independently developed this field. Their work established a new way of studying geometric objects using a coordinate system, a foundation that still stands strong today. Our journey continued through the evolution of analytical geometry. We saw how it has grown and adapted over the centuries, continually expanding its reach. It's not just a chapter in a math textbook, but a living, breathing entity that continues to evolve and shape our understanding of the world. We then dived into the power of coordinates. We discovered how they represent geometric shapes and solve problems, serving as an essential tool in modern mathematics and its applications. From plotting a simple line to visualizing complex three-dimensional figures, coordinates give life to abstract mathematical concepts. Analytical geometry isn't confined to the realm of academia. Its influence seeps into various fields, from physics and engineering to computer graphics. It helps us design bridges, create realistic video game graphics, and even predict the behavior of subatomic particles. It's a testament to how mathematics isn't just about numbers and equations. It's a language that helps us understand and navigate the complexities of our universe. In our daily lives, we are surrounded by the fruits of analytical geometry. Every line, curve, and figure we encounter, whether on a blueprint or a computer screen, is a testament to this powerful branch of mathematics. Remember, every time you see a geometric shape, a coordinate system, or an algebraic equation, you're seeing the work of centuries of mathematical thought, all thanks to analytical geometry.